Hello everyone. In this video, we will discuss the key concepts of the ADAM method as an optimization algorithm. As you know, in the real world, we face challenges such as high-dimensional problems, noisy data, and ill-conditioned terrains. Ill-conditioned terrains refer to poorly conditioned functions, meaning functions with highly unbalanced or uneven gradients. This method was introduced in 2014 by Diederik P. Kingma and Jimmy Ba as a stochastic optimization method at the International Conference on Learning Representations (ICLR). The motivation behind proposing this method is that earlier optimization algorithms, such as SGD, Momentum, and RMS-Prop, face several limitations and challenges. The first issue is the use of fixed learning rates. The learning rate refers to the step size taken by the algorithm at each iteration to move closer to the optimal point. In regions of the objective function with small gradients, a larger step size can accelerate convergence, while in regions with steep gradients, a smaller step size improves accuracy and stability. Therefore, relying on fixed learning rates becomes a significant limitation of earlier optimization methods. Another challenge is the convergence speed in sparse or non-stationary problems. The final issue is the difficulty of controlling noise or ill-conditioned gradients. The core inspiration behind this method is the combination of the benefits of two optimization techniques, Momentum and RMS-Prop. The Momentum method utilizes the first-order moment, namely the average of past gradients, which helps smooth gradient updates and accelerates convergence. Similarly, RMS-Prop leverages the second-order moment of the gradients, that is, the variance of the gradients, and scales the parameter updates accordingly. Therefore, as discussed so far, the main innovations of this method include the introduction of adaptive learning rates for each parameter, the use of bias correction to stabilize updates, especially during the early stages of training, and the simultaneous use of both first-order and second-order moments. The impact of this method on machine learning has been substantial, as it has been widely adopted in frameworks such as TensorFlow and PyTorch. Moreover, due to its robust performance across diverse architectures, including CNNs, RNNs, and transformers, and its ability to handle sparse gradients and noisy data, it has become the default optimizer in deep learning. In this section, we examine the impact of the ADAM method on real-world optimization challenges. The first challenge, as mentioned earlier, is high-dimensional problems, which lead to slow convergence in large parameter spaces. ADAM addresses this issue by using adaptive learning rates for each parameter, thereby improving the convergence speed. The second challenge is ill-conditioned terrains, which, as discussed, cause zigzagging behavior in steep regions and slow progress in flat regions. Since ADAM incorporates the Momentum method, it smooths the updates, while adaptive scaling adjusts the step size appropriately. The third challenge involves noisy gradients, which result in instability and oscillations. Through the use of Momentum, ADAM reduces the effect of noise, and gradient scaling further stabilizes the updates. Another challenge is sparse gradients, which can lead to wasted effort on irrelevant parameters. ADAM mitigates this issue by focusing updates on significant parameters through adaptive learning rates. Finally, the challenge of hyperparameter sensitivity, where poor tuning may cause divergence or stagnation, is alleviated in ADAM by robust default values and adaptive parameter adjustments. Up to this point, we have presented the overall framework of the method and identified the key features of the ADAM algorithm, which can be summarized as follows. It is an iterative optimization method designed for unconstrained problems. IT combines Momentum, which smooths parameter updates, with adaptive learning rates that scale step sizes. IT tracks both the first moment, the mean of gradients, and the second moment, the variance of gradients. That it performs well in the presence of noisy gradients and ill-conditioned optimization problems. Finally, it is efficient and computationally inexpensive. To further demonstrate the effectiveness of this method compared to other optimization techniques, this section provides a brief comparison with several well-known optimization methods based on key features, as summarized in the table shown here. As can be seen, similar to quasi-Newton methods and unlike Newton-based methods, this algorithm requires only first-order gradients and does not need second-order derivatives, namely the Hessian matrix. Moreover, two major advantages of this method over Newton-based methods, quasi-Newton methods, and line search methods are its ability to handle noisy gradients and its use of adaptive learning rates. In addition, this method exhibits high computational efficiency, whereas Newton-based methods have low efficiency due to the need to compute the Hessian matrix, and quasi-Newton methods have moderate efficiency because of Hessian approximation. The final advantage is its ability to scale to large dimensional problems, which is supported by this method but is limited in the other approaches. Now, to explain the algorithm step by step, we first define its symbols according to the table. G sub t is the gradient at each iteration and must be computed at every step. M sub t is the exponential moving average of the gradients, also known as momentum, and it is initialized to 0. To v sub t is the exponential moving average of the squared gradients, representing the variance, and it is also initialized to 0. M hat sub t and v hat sub t are the bias-corrected momentum and bias-corrected variance, respectively. These are computed to ensure more stable updates, especially during the early stages when m sub t and v sub t are very small. Alpha is the learning rate, with a default value of 0.001. Beta 1 is the decay rate for the momentum term, with a default value of 0.9. Beta 2 is the decay rate for the variance term, with a default value of 0.999. Epsilon is a small constant used to prevent division by 0, and it is typically set to 10 to the power of -8. In this section, we explain the algorithm step by step. I in the first step, we compute the gradient of the objective function. I in the second step, we update the exponential moving average of the gradients, also known as momentum. In this step, the effect of the gradients on the update direction is taken into account. Momentum accumulates gradients with exponential decay. The decay rate for momentum determines how much influence the current gradient and the previous gradients have. I in the third step, we update the exponential moving average of the squared gradients, which represents the variance. In this step, the effect of variance on the step size is considered. Variance accumulates squared gradients. The decay rate for variance determines how much influence the current variance and the previous variances have. I in the fourth step, we compute the bias-corrected momentum and bias-corrected variance in order to eliminate bias and ensure more stable updates. Finally, in the last step, as shown in the formula, the step size at each iteration is computed, and the parameters are updated using the corrected values. To help clarify the algorithm, we present an example in this section. As a first step, we compute the gradient of the objective function. As you can see in the initial step, we first compute the value of the objective function at the starting point. Then, in the first iteration, we compute the gradient of the objective function at the initial point. I in the next step, we compute the exponential moving average of the gradients, also known as momentum, according to the corresponding formula. As mentioned earlier, the exponential moving average of the gradients is initialized to 0, and the decay rate for momentum is set to its default value of 0.9. After that, we compute the exponential moving average of the squared gradients, which represents the variance according to its formula. Similarly, the exponential moving average of the squared gradients is initialized to 0, and the decay rate for variance is set to its default value of 0.999. Next, we calculate the bias-corrected momentum and the bias-corrected variance, and use them to update the parameter. After that, we evaluate the objective function at the new point. Then, in the second iteration, all the previously described steps are repeated. This includes computing the gradient, computing the first moment, computing the second moment, and applying the bias corrections based on the updated parameter obtained from the first iteration. The parameter is then updated again, and the value of the objective function is computed at the updated x. The algorithm continues to iterate until convergence to the optimal solution. The table shows the results of the example for the first 7 iterations. This figure is also provided to schematically illustrate the convergence behavior and the optimization path. Thank you very much for your attention and for taking the time to watch this video. We hope this educational video has been helpful and that you found it informative.